Good morning, students. So today we are going to discuss the 3D problem, which is nothing but hydrogen atom. So 3D problem, we are talking about 3D problem. It's a three-dimensional motion around the nucleus, and we are going to have two 3D problems. One is a hydrogen atom, then another one will be rigid rotator in the next class. So in the last few classes we discussed about the one-dimensional problem, like quantum well problem, barrier problem, infinite quantum well problem. So we solved a extraordinary equation for wave function and energy eigenvalue. So these are all one-dimensional problem. It's easier to solve. Whereas this belongs to hydrogen atom and rigid rotator. They belong to three-dimensional problem. So it's very difficult to solve difficult to solve extraordinary wave equation. So we'll have to only go for spherical polar coordinates. So in spherical polar coordinates, we are going to separate so each coordinates like r, theta, phi. So we are going to separate using separation of variables techniques. We are going to separate all the three coordinates r, theta, phi. So that's the idea behind. But hydrogen atom, the problem arose from Niels Bohr. So atomic structure. So in the year 1913, he only put forth the structure of the atom, which we follow now. Niels Bohr, he was a Danish scientist. So full name is Niels Henry David Bohr. He was born in Copenhagen in Denmark in the year 1885. He was the second child in the family. He was having one elder sister and younger brother. His daddy was a physiology professor. His mummy was a Jew. She belongs to a wealthy family. She was a Jew, wealthy family, very, very rich. So totally his family was very, very rich. So his brother and Niels Bohr and his brother both were football players. They were so interested in playing football. So they joined the school nearby their house, and the school was very, very strict. So automatically he had to learn all the subjects very well. His father was a professor in the university there nearby, and usually he will bring all his friends or professors to his house. So at home they used to talk only subjects along with his daddy's friends. So automatically you will come to know some science, philosophy, arts. So he was very studious. And when he was doing his graduate at University of Copenhagen, the Royal Society of Denmark, they announced one competition. This is about writing the paper. So writing the research paper on the measurement of surface tension of liquids and solids. So he was also interested in, Niels Bohr also was interested in writing the research paper. So night and day he worked very hard to find out the new experimental ideas on the measurement of surface tension of liquids and solids. In fact, he used his daddy's laboratory at night, whole night, tirelessly. So because of his obsession for the experiment, his daddy was much more worried, because throughout the day, throughout the night, he was working very hard in the experiment, doing some new ideas. He was much more worried. He asked him to stop. Come on, it's enough. You concentrate on studies. But he did not listen to his dad. He went to his daddy's house, grandfather's house. Again he did the same experiment. For the next 6 months, he completed the project and sent the paper to Royal Society of Denmark. And the results came he got gold medal for the paper. So he was very, very famous at the time. Even he did not graduate, undergraduation, but however, he competed with all graduated scientists and he got gold medals. So 1907, in fact, he finished his undergraduate. 1909, he finished his postgraduate in physics. In undergraduate and postgraduate, he studied physics, maths, chemistry, and of course astronomy. So major subject was physics. Then in the year 1909, he started doing his research work. He joined PhD. He submitted his PhD in the year 1911 on the electron theory of metals. So at the time, the Drude laws, they were all very famous. Electron theory of Drude laws, they are very famous. So after the submission, he got PhD awarded. Then after that, on invitation, he went to UK and he met J.J. Thomson, famous J.J. Thomson, and he worked under him, and it was very hard to work under him, and he was so strict. J.J. Thomson was so strict. Also, he pointed out some mistakes in the book which was written by J.J. Thomson. So both did not get a very good opinion. Both had they have a lot of difference of opinion. So after that, in the year 1912, he joined under Rutherford, Ernest Rutherford, which we know already, the planetary model. It was introduced by Rutherford. He joined under him in Manchester, University of Manchester. There he worked together as postdoctoral studies. So they were friendly with each other and they started doing a lot of research work. Again he came to Denmark, 1912, he got married. He learnt a lot of things from J.J. Thomson as well from Rutherford. Then in 1913, he wrote a paper on atomic structure. It was very, very, very famous. It became very, very famous. So 1913, the structure of the atom. In fact, he took the ideas from Planck as well from Einstein. He extended those ideas. Planck said about the quantization of energy. In black body, we know that the energies are coming out as resonators, and Planck's idea was the quantization of energy. The energy was quantized. Whereas in Albert Einstein idea will be light is quantized, photon is quantized. Bohr said the energies in the atoms are quantized. So we are going to see whether really it exists or not. So he introduced the Bohr atom model in the year 1913. So very, very famous. So 1916 in Denmark, he joined as a professor in University of Copenhagen, and he himself started a new research institute in Copenhagen, theoretical physics, and he became the director. For 46 years he had been there. So he was working as a professor as well as director of the theoretical institute in University of Copenhagen in Denmark. 1922 he got the Nobel Prize for the development of structure of the atoms as well as for hydrogen atom, which we are going to see. So hydrogen spectra was first displayed by Niels Bohr. So very, very famous. He became very, very famous. In fact, he worked along with the famous scientists Heisenberg, Schrödinger, Pauli, and he had some difference of opinion with Albert Einstein. In fact, they both fought. They had lot of different opinions. They had some quarrels, not for themselves but for the science. So one was about deterministic, another one was about probabilistic. He was a probabilistic nature. Einstein was deterministic. So both had different opinion. So 1922 they had lot of discussions about the development of quantum theory. So he developed quantum theory along with Heisenberg, Schrödinger, and in the Solvay conference 1927 he announced the new theory has been evolved in the era That's called quantum mechanics. So he himself said in the conference. So that was a remarkable one. That's why we always say that he is the godfather of quantum mechanics. So 1933, when Hitler came in power, and he got in trouble because his mother belonged to Jewish family. So basically he was a Jew. So they want to capture Denmark. They came, and his family along with sons. He had 6 sons. 2 of them died earlier. So they had 4 sons. They went to Sweden. Then after that, himself and his son fled to United States. His son, after that, his son got Nobel Prize. 1975, his son got Nobel Prize for the development of theory of structure of nucleus, atomic nucleus. He got the Nobel Prize for the atomic structure, whereas his son got Nobel Prize for the theory of structure of atomic nucleus. His son, eigen Bohr, Bohr. People say eigen Bohr. So now 1975, he got the Nobel Prize. His son also got the Nobel Prize. So after the war, again he came to Denmark, and he served up to 1962. He passed away at the age of 77. So Bohr was very, very famous about atomic structure. Still this atomic structure exists. Okay, still the theory exists, and this is the portrait of Niels Bohr. So he has given a lot of contribution to science, especially quantum mechanics. Okay, so we are proud to have Niels Bohr here on the picture here. Okay, so we will talk about hydrogen atom today. Hydrogen atom, as I said, this is a 3-dimensional problem. So we have to take Schrödinger time independent wave equation. So this is Schrödinger time independent wave equation we will have to take. So this is 3-dimensional problem. As usual, the problem goes like this. So we have 3 coordinates. Using the separation of variable technique, we are going to eliminate all the 3 coordinates independently. So we will have 3 equations carrying each coordinate. So that's the idea. Okay. So this we have already seen earlier in the previous class. Okay, the technique that we have used in the previous system of particles. Okay, so the potential energy is given by the attractive force. Okay, so between an atomic nucleus of charge plus E and electron charge. So you have the simplest atom. You have an electron and a proton. So there will be attraction between these two. Correct? For a hydrogen atom. For hydrogen atom, we have a single electron and a proton. Correct? In some other atoms, the outermost electrons, they may have only a single electron. And we can consider this as a hydrogen-like system. We can consider those atoms as hydrogenic system, hydrogen-like systems. So hydrogenic systems. Okay, is it clear what I am saying? So hydrogen atom, hydrogenic system, hydrogen-like systems. So that also will obey the same rule. Okay, in fact he did a lot of experiments on hydrogen atom, especially hydrogen atom. He found out Bohr radius. For the first time, the radius of the hydrogen atom found out 0.53 angstrom. Okay, how it is possible? You have a tube and filled with some hydrogen atom. You are going to give some high power voltage. You are going to give high power voltage. So if you are going to pass some light, immediately you can get some spectrum on those sides. Okay, the spectrum which was observed was not continuous but discrete in nature. So he could obtain the spectrum as discrete lines which are apart, discrete lines. From the lines we can get wavelength, from wavelength we can get energy, from energy we can get velocity and radius. So this is what he obtained the Bohr radius as 0.53 angstrom. Is it okay? Bohr radius. He was very, very famous for Bohr radius. And also zirconium. You heard the element zirconium. So after that it was named after Bohr as borium. So 107th element in the periodic table, 107th element is borium. So named after borium. Also he was very, very famous for complementarity. Complementarity, the concept of complementarity goes like this. So when we are going to have the quantum particle, the dimension is very, very less, and the quantum particle will be associated to the wave. So we will think whether it is a particle or a wave. We will think. But the experiment says, depending on the experiment, it can be a particle or it can be a wave nature. We cannot have both at the same time. We cannot measure particle and wave at the same time. So this is called complementary nature. So this was introduced by Bohr too. Okay. And now we are going to have this. This is coordinates. Okay, ordinary coordinate system. We are going to have into spherical polar coordinates. So we are going to change into x, y, z as r theta comma r theta phi. So 3 coordinates. Okay. Now the spherical polar system is exactly drawn on the figure. We have theta. Of course, first we will go with r. R is a radial part. So you have a nucleus, proton is here, and electron is here. You have a radial part. Correct? This is your radial part. An angle between your z component and r, that will give the polar angle theta. Okay. So theta. So theta will vary from this side to that side. Okay, this side to that side. It means theta will vary from 0 to pi. R goes from 0 to the maximum distance of the atom, which is nothing but capital R. So we can consider this as infinite. So R has a limit 0 to infinite. Theta has a limit 0 to pi. Okay. Now what are these phi? Phi is the azimuthal angle. And you just make a plane. This is a plane. Plane on xy plane. See, you have a plane on the xy plane. Okay, just make a line. So that's a plane. This plane will rotate like this. Full rotation. 2 pi rotation. This is your phi angle. So phi angle will have 0 to 2 pi. The limit for phi will be 0 to 2 pi. So we have 3 coordinates. R goes from 0 to infinity. Theta goes from 0 to pi. Phi goes from 0 to 2 pi. Okay, you have to remember. Okay, this is about the spherical polar coordinates. And of course, we are going to assume that V of r vector equal to V of r, which is nothing but spherically symmetric. The potential that we are going to consider is spherically symmetric. We know about spherically symmetric earlier, correct? We have already studied about the spherically symmetric potential earlier. The magnitude that, for example, just take magnitude from the fixed point is constant. We have the direction and magnitude. The motion of the particle, we will consider in that way. Its magnitude from the fixed point will be always constant. Okay, it depends only on the magnitude, does not depend on direction. So V of r vector equal to V of r. So we have to assume this. And the Schrodinger equation in spherical polar coordinates can be written exactly like this. So we know already this one. Okay, spherical polar coordinates. So you have r part, here also r and theta part, r theta phi part, and we have, okay, no coordinate systems. Okay, we'll think it out. Now we are going to eliminate r, theta, phi separately. So that's the idea. Now multiply throughout by r squared sine square theta. So equation 2.247, you multiply with r squared sine square theta. So r squared will cancel. You have sine square theta partial d by dr, r squared d psi by dr as it is. So r squared sine square theta. Okay, you are going to multiply r squared sine square theta. So r squared 1 sine theta will get cancelled. You have sine theta d psi by d theta. Okay. The next term will be, you have r squared sine square theta, both will get cancelled. What is the idea? Why should you multiply with r squared sine square theta? To get this part alone. Okay. So now look at this one. This has no r part. This has no theta part. Only it depends only on phi part alone. So that's the idea. Now 2m r squared sine square theta by h bar squared e minus e psi. Okay. This equation gives us a wave function. So our ultimate aim is to find out, as I said, wave function and energy eigenvalue. So that is the ultimate aim. Okay. So as I said, in one dimension, we can easily solve Schrodinger equation to approach wave function and energy eigenvalue. In 3 dimension, we need to have all the 3 coordinates. Okay, we need to have all the 3 quantum numbers. In 1 dimension, we need to have only principal quantum number alone, n alone. But here we are going to have all the three quantum numbers n, l, m. We are going to describe what is n, l, what is l, m later. Okay. Now using the separation of variable, the splitting of the equation to different parts with only one variable in each part is called separation of variables. Okay. Now just introduce the wave function, which is nothing but radial part and angular parts. The product of radial part and angular parts. So these are all called angular parts. This is nothing but your radial part. R of r is the radial part. Theta of theta is theta part. Phi will be your phi part. Okay. The product of these two will give you angular part. The product of these two will give you spherical harmonics. The product of these two will give you complete wave function. Okay. And this is called a angular part, YLM. So there must be R of r must be there. Okay. Here there is a mistake here. Your R of r, YLM theta comma phi must be there. Okay. And this YLM theta comma phi is called spherical harmonics. Okay. Now you just differentiate. Now we are going to differentiate this wave function with respect to r, with respect to theta, with respect to phi. Because in the earlier equation we have, see, d psi by dr. We can differentiate with respect to r. D psi by d theta. We can differentiate two times to get d squared psi by d phi squared. So that's the reason that we are going to differentiate this wave function in terms of r, theta, phi. Now just to differentiate. So now differentiating with respect to r, that will give you dr by dr. Those two things are constants. Correct? Theta and phi are constant. So pull it out. So we have dr by dr. Okay? So similarly d psi by d theta will give you r and phi, you pull it out. So they will become constant. So d theta by d theta. D psi by d phi will give you r theta d phi by d phi squaring, because we need to have a squaring value. Correct? So that's why just square this one, that will give you the r theta d squared phi by d phi squared. Now substitute this one in this equation. So we will get like this. Okay? We are going to substitute. Look at this for example. So this is the first expression. We are going to substitute here in this expression. Okay? See, d psi by dr. So d psi by dr. Instead of d psi by dr, you substitute theta phi dr by dr. You will get this. Correct? Theta phi sin square theta d by dr, r square dr by dr. And that will be your second expression. This will be your third one, and this will be fourth one. Now divide by r theta phi. Okay, divide by r theta phi. So r theta phi, the same equation, you are going to divide this equation by r theta phi. Theta phi will get cancelled. We have 1 by r. So we have 1 by r. So sin square theta by r d by dr, r square dr by dr, plus this r phi will get cancelled. You have sin theta by theta. Correct? Sin theta by theta d by d theta, rest of the terms. Then the next one will be your r and theta will cancel. You have 1 by phi. Correct? 1 by phi d squared phi by d phi squared. And the last term will be 2m r squared sin squared theta. Correct? 2m r squared. We have sin squared theta divided by h bar squared. So here one sin squared theta is missing. Correct? One sin squared theta is missing. So don't forget, you will have to write one sin squared theta. Sin squared theta is here. So you have 2m r squared sin squared theta by h bar squared e minus phi. Is it okay? Equation 2.254. Now just bring this term to right hand side. This term, it depends only on phi. Look at the third term, first term, second term, third term. It depends only on phi. It depends r and theta. It depends only theta. It depends only phi. It depends again r and theta. Correct? So we can bring this term to right hand side. Okay, we have separated now phi term out. So we have separated the phi term out. All the other terms will be in the left hand side. Only one term I am going to bring to the right hand side. Okay, now we have separated phi out. So as I said earlier, so these two equations we are separated, and this must be equal to some constant, like P1 V1 equals P2 V2 equal to some constant, so something like that. So this will be equated to some constant. We are going to equate this constant as ml squared. M stands for magnetic quantum number, L stands for orbital quantum number. M depends on L. So that's the reason ML exists. Okay. So your right hand side is equal to ML square. Okay. And ML has the value 0 plus or minus 1 plus or minus 2. Okay. Magnetic quantum number goes like this. For particular value of L, your M will be minus L to plus L through 0. For a particular value of L, ML has the value minus L to plus L through 0. Is it okay? For example, L equal to 1. Your ML will be plus 1, minus 1 and 0. So 3 values. So that's why I said M depends on always on L. So ML, the value for ML will be exactly 0 plus or minus 1 plus or minus 2. Now you just substitute. So we have ML squared we have found out. Okay, substitute. Right hand side. So we have substituted, correct? Now divide both sides by sine square theta. Divide both sides by sine square theta. So that will give you sine square theta. We have divided by sine square theta. We have divided by sine square theta on right hand side also. And this will get cancelled. You have 1 by r, d by dr, r square d by dr. It depends only on r. Okay, that's the idea. Now what about this term? 2m r squared. So just take it off. That will give you 2m r squared by h bar squared e minus b. So both depend only on r. Okay. Now what is the second term? Second term, it depends only on theta. See, depends only on theta. Okay, both together. So bring this term to right hand side, you will get this. Now look at the equation on left hand side, depends only on r. Right hand side depends only on theta. So again we have separated. Again using separation of variable. So this must be equated to some constant. We are going to equate these two. Okay, is it okay? So we are going to equate to lambda in the next. So we are going to equate this one to lambda. Is it okay? Now we will go for theta part. So we have finished the pi part. Now we are going to have theta part now. So this term will be equal to lambda. So rearranging, that is just multiply by minus sign and bring that lambda term this side, you will have this term, correct? Just multiply with the minus sign, this will become plus, this will become minus, this will become minus, you bring this term here, so this will become plus, so lambda minus this term. Multiply throughout by theta, that will give you this term, okay? Is it okay? Multiply by theta, that will give you this one, equation 2.262. Is it okay? So now, what is this equation? This equation is nothing but Legendre differential equation. The solution will be Legendre polynomial. So easily we can get the solution from Legendre polynomial and apply to this differential equation. Is it okay? So this is already we have studied in special series, in special functions, Legendre differential equation in mathematical physics. So this is your Legendre differential equation and the solutions will be Legendre polynomial. So easily we can solve. Okay. Now we'll solve first pi part. We have approached now radial part. Okay, radial part as well we have obtained now. Okay, theta part. Okay, already we have obtained earlier pi part. So we have separated all the three equations. Okay, now we are going to have the solutions. The solution, first solution will be for the pi. It will be very easier. So just take this equation and bring ml squared this side. That will you will get the equation 2.263. Okay. Just assume the solution, phi of phi will be a e power I ml of phi. Okay, you just take 2 times the differentiation, substitute here, and this equation will be satisfied. We have already done in the class earlier. So this is the solution. Just take the complex conjugate. So a is a constant. So we will have to get the value, normalization constant value. So for that, we will have to use normalization procedure. So just take the complex conjugate. Complex conjugate is given by this equation and take the normalization constant. As usual, this is a procedure we know already. 0 to 2 pi. Phi goes from 0 to 2 pi. Already we said discussed. So 0 to 2 pi, normal function multiplied by its complex conjugate d tau. Okay, d tau. Here it is d phi. So d phi limit will be 0 to 2 pi. You pull a squared out. So you substitute these two and take a squared out, that will give you this. Both will get will become 1. You have a mod a square d phi, and substitute the limit, you will get 2 pi, correct? A square 2 pi. You substitute d phi, integrating d phi, you will get pi. Pi limits from 0 to 2 pi. So 2 pi minus 0, you have 2 pi a square. So mod a will be 1 by 2 pi. Your complete wave function with the normalization constant will be phi equals 1 by root 2 pi e power I m alpha. So we have solved one equation. Pi part of one we have solved. Okay. Now we will go for the second one, theta part. Theta. Okay. So for that we are going to solve the theta equation. For that we are going to assume z equals cos theta. We are going to assume. So just to differentiate, that will give you dz equal to minus sin theta d theta. So this is your theta part, correct? This is the theta equation. We are going to solve. So you just bring this d theta down, dz down. You differentiate on both sides. That will give you d by d theta equals minus sin theta d by dz. This we have already seen in the earlier class. The same procedure. Okay, which is equal to, of course we know sin theta equals 1 minus cos square theta to the power 1 by 2. So this minus is here, 1 minus cos square theta, correct? Already cos theta is nothing but z. So cos square theta is nothing but z square. So you have minus 1 minus z square to the power 1 by 2 d by dz. So this equation 1 divided by sin theta is nothing but 1 minus z square to the power 1 by 2, correct? Your d by d theta is nothing but minus of this factor. So you have minus of 1 minus z square to the power 1 by 2 d by dz. Is it clear? So this part is over, correct? This part. So sin theta. What is sin theta? 1 minus 1 minus z square, correct? Sin theta will be 1 minus z square to the power 1 by 2. Then d by d theta will be multiplied by minus 1 minus z square to the power 1 by 2 d theta by dz. So this expression, complete expression is given by this one. So plus lambda minus ml square divided by 1 minus z square for sin square theta. Is it okay? Now this one and this one will cancel. Minus into minus plus. So plus d by dz. This multiplied by this will give you to the power 1. This is to the power half, this is to the power half. So this will give to the power 1. As usual, d by dz. So t theta by dz. Plus the next term as it is like this. So this is for associated Legendre differential equation. Okay. So for certain limits, we know already, we have discussed the 4 mathematical functions: Hermite differential equation, Legendre differential equation, Laguerre differential equation, and Bessel function. We have already discussed. So they mainly depend on the limits. Limits are different. For Legendre differential equation, we have already studied that the limits will be minus 1 to plus 1. Here cos theta exists, correct? Z equal to cos theta. Cos theta has a maximum value plus 1, minimum value minus 1. So that's why the poles are at plus 1 and minus 1. That's the reason. Okay. So now defining lambda equals L into L plus 1. We have already defined earlier this lambda, which is nothing but L into L plus 1. L stands for orbital quantum number, and which has the value 0, 1, 2. Okay, 0, 1, 2. M depends on L. Okay, L depends on N. Okay, we will see. We are going to see. N is the principal quantum number, L is the orbital quantum number, M stands for magnetic quantum number. Okay, the solution of equation 2.272, the previous equation, is Legendre polynomial, which is given by PEL of Z for m equal to 0, and associated Legendre polynomial PEL mod m for m is not equal to 0. So we have both the things, m equal to 0 as well for m is not equal to 0. The normalized solution is given by this expression for theta part. So this is your Legendre polynomial, normalized one. So this is your normalization constant. Of course, this part will be your Legendre polynomial. So how to find out the normalization constant? We have already studied in mathematical physics earlier. So using this expression, correct? Pk of m, here PLM of m. And the Normalization constant can be obtained using this expression from -1 to +1. The value will be exactly 2 divided by 2l plus 1. L plus mod m with the closed bracket factorial divided by L minus m closed bracket with factorial. Okay. So this is the answer for your normalization constant. Okay. So total part. So theta will be your normalization constant multiplied by the associated Legendre polynomial. Okay. So this is your normalization constant. See here. So NLM we have found out from this. So which is given by this. And PL of mz is nothing but your PLM of cos theta. And of course it depends on your small epsilon. Epsilon is equal to -1 to the power m when m is greater than 0. For m is less than or equal to 0, this must be equal to 1. So you should round 1. So now we know already this angular part is nothing but spherical harmonics, which depends on both theta and phi. So YLM theta comma phi. We have solved for theta, we have solved for phi. The product of these two will give you complete wave function for angular parts. Okay, angular parts. So which is nothing but your theta part multiplied by angular part. See, your theta part. This is your angular part, which is nothing but YLM theta comma phi. Is it okay? You are going to multiply this and this. The product of wave function of phi part and theta part will give you the complete solution for your spherical harmonics, which is nothing but YLM. Is it okay? Where L goes from 0, 1, 2 and M goes from 0 plus or minus 1 plus or minus 2 up to plus or minus here. Is it okay? Now e power IML of phi makes spherical harmonics usually bit complex. I factor is there. But it will be always good when you work with real numbers, real form. Now we will go for the radial.